I'm almost out of storage space on this camera, which is fine. I can just delete stuff off. But so anyway, what that means is I'm probably only going to get one, maybe two more videos on here, and that's fine. I should be able to get finished. This is, again, lecture 10, and I think this was, I'm hoping this is page 4. This is L10, page 5. So we were talking about, again, got water in my cup. If I don't stir it up, if it's just sitting there stationary, what types of energy does it have? Well, it has internal, kinetic, and potential. Okay? Very important question. I always do this when I'm trying to explain this to a class. Is this water flowing right now? No. It's not flowing right now. How do we make it flow? How do you make this water flow? You pour it out, right? That's one. What if I had a straw? How does a straw, which I should go grab a straw, but I don't have one handy. If I had a straw, how do I make this water flow? And one might say, well, you suck into the straw. Yeah, you don't technically pull a fluid. I mean, you can kind of think about it. You push a fluid. Right? So if I put a straw in here and I put my mouth on the end of the straw, what I do with what you're doing when you drink out of a straw, you're actually lowering the pressure within your mouth so that the atmospheric pressure outside pushes the surface of the water up into the straw. And if you continue to lower the pressure inside your mouth, you will create a vacuum that will draw the water up using the atmospheric pressure outside. It's easier to push a fluid really than almost impossible to pull it, but you can push it. And so if you can use atmospheric pressure to push the fluid up into the straw, that's how you use a straw, right? So you push with pressure. This applies a force over a distance. Right? So it's additional energy being done. It's the work. This is what we call the work done by upstream fluid. Right? If I have some kind of a conduit and I have flow moving through, what keeps these molecules in here flowing? Well, it's because I've got molecules upstream pushing, applying pressure to the molecules downstream constantly, and this text likes to draw this imaginary piston cylinder applying this pressure to the fluid downstream, spread across this area, so to speak, and applies that through that area over length L, right? And so what it does is it says, well, that pressure times area times length is equal to pressure times volume, or pressure times specific volume per unit mass. So, what types of energy does flowing fluid have? Well, the same as the water sitting in my cup. Internal, kinetic, and potential. But the difference, because this fluid in here is not stationary, something's pushing it. Something's adding additional energy to it. The pressure upstream times the volume gives me basically the work done by the upstream fluid. Because otherwise it doesn't flow. This is not flowing, it just has these energies. If it's flowing, it has this additional push to get it downstream. That's the difference. So, E dot mass in. The energy rate of mass coming into a system, and it'll be the same thing for out of the system. You're going to have your mass flow rate times the internal energy of the fluid plus the kinetic energy of the fluid plus the potential energy of the fluid. Okay? Internal, kinetic, potential. But then there's also, and again, if it's stationary, that's all it has, but it's not stationary. And the reason it's not stationary is something is pushing it. The fluid upstream is pushing it, trying to push it downstream. Now, you're welcome to go look up in your property tables a U value and then look up and find the product of pressure and specific volume and then add all these up. I might suggest to you that's already done for you, or part of it's already done for you. U plus PV goes by a special name. We call that enthalpy. It's the energy of flowing fluid. So for control volume, for when we're talking about the energy of mass in or the energy of mass out, because again, that mass has its own internal kinetic and potential energy, but because it's flowing, it's being pushed, so it has this PV term. So we will use H's when we're talking about mass coming into or out of a control volume to track its energy. So mass crossing the boundary, because it's flowing, has an H value, not just a U. Okay? Alright, so with that in mind, let's talk about the first law for steady flow control volumes. Well, the pure, unadulterated first law says that the total rate of energy in minus the total rate of energy out, E dot in minus E dot out, equals dE dt, the change in the energy for our system with respect to time. Now, if it's steady flow, right? If it's steady flow, that differential goes to 0. And if we talk about all the ways energy can come into or out of a system, well, all the ways energy can come into a system would be heat, so I've got a heat rate, plus W dot in, that's the power rate. Right, so we call a work rate, we call that power, plus E dot mass in. Minus all those things going out, minus Q dot out, minus the power output, minus E dot mass out, equal to 0. Now, we need to expand that just a bit with this in mind. Right? With this idea in mind, I can substitute that in here and here. So Q dot in plus the power input plus, I'm going to draw a summation across all of the inlets, m dot times h plus v squared over 2 plus gz. And by the way, most of the time we ignore the potential energy. That's okay. We'll write it for now. And then minus all these things going out. Q dot out minus the power output, w dot out, minus summation of all the outlets, m dot times h plus v squared over 2 plus gz. That whole sum, if it's steady, if it's flowing steady, the change, the right-hand side, is 0. Add all the ins, subtract all the outs, that equals 0, if it's a steady flow control. Now, this is kind of the most generic form of the first law we will use in Chapter 5. It's not very often that I'm going to have multiple inlets and multiple outlets. In fact, it's probably rare for what we're going to do in this course. If we have one inlet, we'll call him 1, and one outlet, we'll call him 2. We can simplify this just a little bit. if I have one inlet, if we look at the conservation of mass, let's do that. Let's look at the conservation of mass first. Well, the conservation of mass, I've got one inlet, one outlet, and it's flowing steady. And we say the sum of m dot n is equal to m dot 1, the mass flow rate n. And we say, so we'll say and, sum of m dot out is equal to m dot 2. So we say, well, m dot 1 coming in minus m dot 2 going out is equal to dm system dt, and if it's flowing steady, that goes to 0, which tells us that m dot 1 is equal to m dot 2, and we'll just call that m dot. So if I have one inlet and one outlet, and it's steady flow, the mass flow rate in is equal to the mass flow rate out. We'll just call that m dot. So notice the first law gets a little bit simpler if I've got a steady flow control volume with one inlet and one outlet. I can say this. I can say Q dot n plus the power n, W dot n, minus Q dot out minus the power output, W dot out. And then I'm going to group my masses together. So I don't need a summation because I've only got one inlet and I've only got one outlet, and they have the same m dot between them. So I'm just going to say plus m dot times quantity. I'm going to say h1 minus h2, that's n minus l, plus v1 squared minus v2 squared, both over 2, that's kinetic energy in minus kinetic energy out. And if we're considering it, it's probably negligible, but there is a potential energy change, G times Z1 minus Z2, close quantity, and if it's flowing steady, that's equal to 0. This is the most common form of the first law for for control volumes, for steady flow control volumes, that we'll use in Chapter 5. Like we saw with the first law equation that I highlighted at the beginning of Chapter 4 and said this is the most common form we'll use in Chapter 4, notice how often we used all of these terms. Pretty rare. It's pretty rare we used all these terms. That's going to be the same thing in Chapter 5. It's going to be pretty rare we're going to use all of these terms. Okay. And I think I have, I am running out of voice, so I'm going to quit there. That is plenty. That's probably too much, but I appreciate you guys toughing it out. If you made it this far, you're doing good. Keep up the good work. We're going to get through this. This is not an easy class. I don't try to make it hard. I hope you guys understand that. I hope you guys see that. I don't try to make this class hard. It's a lot of work. It's a lot of effort. And we expect you to start learning how to solve problems. And that's the tough part, learning how to solve problems. Just practice. One thing I'll mention, I'll put this at the beginning of the next lecture. Okay? That's plenty for the week. You guys have a good weekend, unless you're behind on watching these, and then have a good, whatever your next rest period is. All right, guys. Have a good one. Bye-bye.